Okay, so I'm back here looking at the JP Morgan Chase Python training course, and I've gone into the GitHub, and specifically I'm going to the notebooks, and I'm looking at the Straddle. So this is number two, and I'm looking at the Straddle strategy. It's an option strategy where you combine both a call and a put together. And just for reference, I will leave a link also to how you would set that up in in Excel, right? Just so basically, I followed the approach suggested by John C. Hull, Option Futures and Other Derivatives from his textbook. I'll leave a link to that textbook as well. But just in terms of how you would configure the trading um, strategy where you combine a call and a put position and what that gives you in terms of a trade. And we might note as well, historically, going to Weber, 2008, these trading strategies have been around a long time. So, for instance, the long straddle combination was known about, and traders were using it both Paris and London, according to Moser in 1875 and Lefebvre 1873. And they basically put out in those original pamphlets they released, um, they describe exactly how you would configure a long call and a long put. Okay, so these trading strategies actually have some history and some legacy, and just to point that out. Okay, so I'm interested here in setting this up in Google Colab. So there's interesting things going on, and I'd like to try out the code. But of course, you can't execute the code in the GitHub because it's sort of on ice. It's supposed to be locked and we don't mess around. But we would like to play with the code. And to play with the code, this Python code, just copy the URL link, go into if you Google Colab. I'm going to use Google Colab. You need to have a Gmail account or a Google account. So we'll create a new instance of this a Jupyter notebook using Google Colab. And because the code is available in GitHub, we can point Google Colab at the specific URL we're interested in. So remember, we're copying the hyperlink to URL here, and then we're pasting in, and it's already has pulled in the links. So I'll just open up this one, and everything here is good to go, right? So even the formulas actually come in, and they're intelligible. We can observe what's going on here, and we can run the code. Now, to run the code, um, it's good if you want to save your work, the changes that you've made. So file, save a copy as, and then depending on the type of conventions you have for filing or storing away particular Jupyter notebooks, I normally put a date because I can trace back what was going on based on a timeline. That normally is quite intuitive for me. So I'll just save with the date and I'll file save. And that saves in my Google Drive. If I want to go back tomorrow, take a look at the work I've done or any changes I've introduced here, I can do that. And I have full editing capability. So if I double click here, for instance, and let's say there's something over here, I felt, oh, it should have been one. That's not a two, it's a one. Now it's a two. But if I introduce the change here, I can edit the formula according to whatever specific needs that I have. So we have 2 over square root of 2 pi, and that's consistent with what actually was proposed here. Now, does the code work? Okay, code, let's try it out. So we create these objects. So maybe read something using some more complex but still simple operations. We can approximate the ATMF straddle. And I leave a link here as well. I'll post this Colab up with the changes I've made. I won't put everything in, but I'll run a few of the cells here, and then I'll go back and give a more kind of grounded context to what the straddles are supposed to accomplish and how we might be able to estimate the premium associated with a straddle. Okay, so let's run the code cells and see what happens. Now, this would be the volatility, so the annualized volatility of the return, and the maturity on the options, where you have a shared maturity for the call and the put that share the same exercise. And then we're trying to implement this segment of this formula here. We're writing up in code, and we're saying, let's execute that and specifically put in the numbers that we identify here. And we have said there's a volatility and time. We create those objects, which then gets fed into this formula, and we get a value of 0.159617. There's a lot to type, I agree. And they say, which is a constant theme in automation, Python automation, there's a lot to type again and again. And if you want to price several straddles, which is really annoying and error prone, let's define a function for this so that we can use it over and over. So if you're iteratively going to produce pricing for straddles and you know the formula, maybe rather than write each estimation in the form of a manual input each time, that you would create a function, a user-defined function, and then further along then wanting and verify that it's correct. So let's just run that. So that defines the function. And then if you come down below here, we can print the output from the defined function, and then print also the manual formula. And of course, we're getting the same result, and they're true. So we're saying print the output from the formula, print the output from the manual estimation using the values we have. And then finally here, the equal sign means just check to see, is this value from the user-defined function equal to the manual estimation? Okay, so it's a nice little demonstration of going from a manual estimation to automating the estimation, where you're setting it up as a user-defined function. Now, also note, if we remove the indentation and try to run that again, won't work. So when you're setting these functions up, just make sure you've indented properly. Now it runs, no problem. And just to check and test that our results, the user-defined output is the same as the manual output. Yes, they're still the same. Input order doesn't matter here, so long as we specify the time is equal to this and vol. But again, a little bit of caution here. If we don't specify the argument, the ordering will be important, right? So this is nice, but what if I want to default to certain inputs by setting the initial inputs below? We're explicitly calling each of these arguments optional. Initially, we'll make some time and optional argument inputs. So we define the straddle. We've the volatility, which is open, but the time we're locking down as being 1 year. And so then if we say straddle pricer 0.2, we've locked in the 1 year maturity. And then we can make explicit where we're saying the volatility is 2 and the time is 1. In other words, we don't need to pass these arguments to call the function. It will use 0.2 vol and 1 for time by default, unless instructed otherwise. So we're getting the same output. And straddler price 0.217. So we're adjusting for the volatility. Okay, notice there's pi in the denominator of Straddle, of the Straddle. So again, if we go back to the formula, there is pi. And in the valuation we've used here, we've used 3.14. That's possibly not ideal. Could we get a more exact or precise value for pi? We could use the NumPy library, so just import NumPy. NumPy is for executing more quickly array operations. And NumPy.py will call in the 3.14 value plus the higher level of precision. And so if we import NumPy, pandas, and datetime, and MP 3.14, and NumPy has a handy square root function. Okay, and then a more exacting measure, rather than set up our function, the 2 multiplied by 3.14 to the power, the double star sign here denotes getting the square root. If we put to the power of 0.5, that's a square root. But maybe we would prefer to make use of the NumPy square root function np.sqrt. Now that's available to us because we have imported in NumPy, and we can also set our function up in a way that explicitly calls in np that takes the square root, and we can also obtain the value for pi and then the straddle pricer. Okay, so let's see what the difference is between our original implementation and our new implementation. So there's a small little change simply because we have higher precision around pi. In this case, the difference in precision and readability isn't huge. I agree, because it's, 0 point and then 4 zeros and then 4. So it's a small number. Okay, in this case, the difference in precision and readability isn't huge, but the difference can be valuable at times. In addition to the functionality above, NumPy can do a lot of other things. For instance, we can generate some random numbers. And so typically, if I generate again, I'll get another random number and go again, another random number. And you can see we don't seem to be exceeding 1 or going less than 0. Okay, so this random number generator is producing a random number that never exceeds, would appear doesn't exceed 1, never falls below 0. Is there a way to see what functions are available? Yes, just tap after MP. Okay, and alternative, you can call dir direct NP to see what's included. Okay, now if let's say you're looking at this and you're trying to, understand a little bit the context here, or maybe there's a little bit of code that you're finding difficult to work through, you could take the code and use ChatGPT as a copilot. So I suspect some things in here I'm not going to understand first time round when I look. Some things will be intuitive. But you may need some guidance as you go through, and we don't really have that available in terms of ancillary resources. But ChatGPT is an excellent resource, and we could go over to ChatGPT and just say, look, Chat, I don't understand. Can you explain the following Python code? Okay, let's just paste in Control V and let's hit return. And it runs through an overview of what's involved. Certainly, the provided Python code defines a function, straddle pricer MC, that calculates the price of a straddle. option using a Monte Carlo simulation. Let's break down code step by step. Straddle pricer is a function that takes 3 optional arguments: volatility, time, daily volatility. It's calculated the result sum. There's a loop that's explained, and then how to execute. So we get a fairly decent overview. Now, not always will we get such a good overview of the code snippet, but we've done a fairly decent job that if there was something in our code that we didn't quite fully understand, we could take the snippet and ask ChatGPT to act as a sort of copilot to just hold our hand and explain what's going on. Or for instance, if I wanted to add something here in terms of other forms of option pricing, and I say, look, I need the Black-Scholes model here because it's a European option, not American option, and I can work out after the valuation. We could go to ChatGPT and say, please write Python code. Please write a def user defined function to estimate the Black-Scholes model. Right? And not normally included, but actually very important, include an argument for dividend yield. Okay, let's see what comes back. Now, I may have misspelled something, but chat generally is quite good and will correct maybe for the issues. Now it's explicitly saying Q equal to 0. Okay. And we have Q. Okay, so that looks, yeah, import NumPy, SkyPy stats, the normal distribution, normal cumulative distribution, fairly full explanation. Okay, so let's just copy this code. Let's see, does it work? Or throw off some errors. Come in here to a code cell. So I'll go back to where we had the option pricing. So I'll say Black-Scholes model, just so that in the table of contents, Black-Scholes model, and just check our table of contents that's it now appearing. Yeah, Black-Scholes model is there. And then we put in a code cell, and the code cell is the Python code. Now, if we run this, it should be okay. Won't run the estimation because we haven't fed any arguments in. We have defined the parameters SKTR, volatility, and Q here. In order to run the estimation, we go back to chat, and there was a second code cell. So let's take that, Control V. And now we've put in 100, 110, T is equal to 1, R is equal to 5%, volatility 20. Okay, I'm going to change this for the moment back to 0 and put K to 100, and the value of the call, this is a call option, not a put. In fact, the call option should be 1045 or thereabout. So let's run this and just verify against it's 1045. So I'm getting the right results. Now, if you didn't intuit what the Black-Scholes model really was here, you could go back to chat and say, please write up in markdown script, a formula for the Black-Scholes model that we used above. And yeah, so please write up in Markdown script a formula for the Black-Scholes model that we used above. That should do it. And see what comes back. Now it'll come back with a script. Actually not. Okay, so I might say, please just come back with a single markdown script for Google Colab text cell. And again, it's a language model, so it's trying to predict what I'm looking for. And this looks promising, and it has a dividend yield that actually would be quite useful. So let's just copy that and see how does it appear in our Google Colab. So I might just put let's close this down. Let's put in the text cell first and then Control V our code. And has it landed? Almost. Yeah, so we might have to do a little bit more refining to get a nice crisp formula here. It's probably something small. I'll chance jet must work in Google Colab text cell this code, this markdown script produces formulas that are not easily readable. And let's hope chat can figure this out for us. Okay, so it's provided us with new. Okay, might work. Let's just copy to see has it created something that is workable. Okay, so I'll double click here and take that out and then Control V. Okay, so it's coming back with something similar. Sometimes we can get a more crisp formula not working here. Maybe if I had used ChatGPT 4, it might have went the extra mile. Although the code here is self-explanatory, but just in terms of what we get here. I'll just pause and I'll bring in code that I have somewhere else. Okay, so if you come over here to Contaro, I better give the Contaro 86 financial models, numerical methods. These Black-Scholes. I could copy that link, and he has quite a nice overview of the Black-Scholes model. I want to import that into my GitHub, right? So what I can do is go Google Colab, and it'll open up a new instance of Google Colab, and then GitHub, and we can Control V. So I've shared the URL, and we'll look for the specific path, and it's found it, in fact. And we can copy the formula here. So if I double click, it'll open up. and it seems to be doing a better job here. So I might just copy that snippet of code, Control C, then go into my formula here and maybe remove everything and go Control V. And you see now we have an impressive enough set of formulas that if I want to edit, I can. So we have this formula here, European option, and we could reconfigure the formula so it looks a little bit more like what we have below. Again, that gives you a sense of how perhaps triangulating between the chat, GitHubs, and Google Colab, you can produce a relatively nice a piece of work in a Jupyter notebook where you run these type of estimations and that you're happy with the notation that's been used. And we have quite sophisticated notation here that could be very useful in setting up your project. You may not want to write everything out, but you have some editing control here, and you can change the formulas by simply going in and introducing minor tweaks to get the formula that you specifically desire. Again, the link there, just to highlight, it's from Contaro, and he's quite an impressive Contaro financial models, numerical models. Really has done a decent job in coming up with a lot of material there. And he also has this ISLR Python project, which is impressive there as well in the repository. So use liberally. It's a free resource, and you can tweak it to suit your own specific needs. Okay, let's leave it there. I'll leave a link to this Colab, and you can come back afterwards and take a look at what we've done here. Okay.